in this section, we finally define projective varieties, at least as sets. And the idea here is the affine varieties that we had before, these were subsets of AN cut out by polynomial equations. And now the projective varieties will be subsets of projective space cut out by homogeneous polynomial equations. And so the definition is, if S is a set inside this ring of polynomials, of homogeneous polynomials, then the projective zero locus or vanishing locus of S is defined just as the set of points in Pn such that F vanishes at this point. And since F is homogeneous, this equation is well defined, as we have seen in the last video. And then subsets of projective space of this form are called projective varieties. And then we have a variant of this for homogeneous ideals. So if J is such a homogeneous ideal, its vanishing locus is the set of points in Pn such that F vanishes at this point for all homogeneous F in J. And so here it's really important, even though this depends on the entire ideal, we just ask the condition where it makes sense, namely for all homogeneous F in J. And so if S is homogeneous, a set of homogeneous polynomials, then quickly follows that the vanishing locus of the homogeneous ideal generated by S is equal to the vanishing locus of S in the sense above. You can check the two inclusions very easily. And so this is a second way to define a projective variety. And then we had these two operations before for affine varieties, the vanishing locus and the ideal. And so we can also define what the ideal of any subset of projective space is. And it is just defined now as the ideal generated by all homogeneous polynomials vanishing on this set. And again, here it's important to take the ideal generated by this. For affine varieties, we didn't have to do this because the problem is otherwise you wouldn't necessarily get an ideal because, for example, the sum of two homogeneous polynomials vanishing on X doesn't have to be homogeneous, particularly if they have different degrees. And so this set otherwise wouldn't be closed under addition. And so once you take the generators here, you of course get a homogeneous ideal inside this polynomial ring. And in the next sections, we will sometimes switch between the ideal and vanishing locus for projective space and for the affine space that we had before. And in the places where we do have to distinguish them, we write IP and VP for the things we have defined above. They result in sets in projective space Pn or in ideals in this ring here. Or when we want to say the corresponding affine constructions, which result, for example, in a subset of A n plus 1, since these are n plus 1 variables, then we write IA and VA. And so to see some examples of projective varieties, we have the same property that we also have for affine varieties, namely that the empty set and the entire set are projective varieties. They're the vanishing loci of 1 and 0, respectively. And if you have a set of R homogeneous linear polynomials, then its vanishing locus inside Pn is called the linear subspace of Pn. And note that we had this map from Kn plus 1 minus 0 to Pn, this kind of quotient map. And then if you take the pre-image of this, of such a vanishing set, then it's just the locus inside Kn plus 1 minus the origin where these linear polynomials vanish. And well, imposing finitely many linear conditions cuts out a linear subspace of this Kn plus 1. And that's basically the reason why we also call this a linear subspace. And this is basically a one-to-one correspondence. So the linear subspaces of Kn plus 1, which are not zero subspace, they just map to these linear projective subspaces of Pn. And then as an exercise, we had these kind of smallest possible sets sets in affine space were just the one-point sets, and we saw these are affine varieties. And similarly, if you have a single point in Pn, and you can show that this single point set is a projective variety, and the exercise is to compute explicit generators for this ideal. And to show you an example, also or looking at what we're going to do in the next few videos, we can write down a single homogeneous equation of degree 2. This one here, x1 squared minus x2 squared minus x0 squared, and see what are the different variants of vanishing loci. And the first one that we're already more familiar with is the vanishing locus, if you see this as a polynomial in 3 variables. And here is copied from Gartmann's notes is the kind of picture of real solutions of this. And what you can see, this equation says basically x0 squared plus x2 squared is equal to x1 squared. So if you fix a value of x1, then this is just a circle of radius absolute value of x1. And in this picture, somehow from left to right is basically the x1 axis. So if you fix a value, then you get here one of the circles on this cone. And then this is the real picture of the affine vanishing locus. And then we can also look at the projective vanishing locus. This now sits in P2. And the interpretation of this is that this is the set of one-dimensional linear subspaces of A3 contained in this affine vanishing locus. That's kind of an you should convince yourself that this is right, because basically well, if you have any point in P2, then this corresponds to an entire line inside A3. And then, because this equation is homogeneous, once a point satisfies this equation, also the entire one-dimensional space spanned by it satisfies the equation. And so projective vanishing locus, you can see it as this set of lines to the origin contained in this locus here. And so what we see is we can draw a picture if we, for example, restrict to this big subset A2, which sits inside P2, because we have seen this sits inside here by setting the first coordinate to be 1. And in this picture here, this corresponds to setting x0 equals to 1. This gives you this plane here. This is very similar to the picture that we had before. And then the solution here corresponds to the line through it. And if you kind of just look at what is the picture in this plane, then you would get this here. Because, I mean, setting the first coordinate to be 1 means you substitute x0 equals 1. And then you get the affine vanishing locus of this. And you can see this is exactly this kind of hyperbola that is drawn here. And so we get this entire hyperbola sitting inside this projective vanishing locus as the points here. But we get a bit more in the projective vanishing locus, because there's 2 lines inside of the affine vanishing locus here, which don't intersect this plane here, because they're parallel to it. And these are these lines A and B here. And in that picture here, as the point kind of goes to infinity along this hyperbola, for example, if it goes to this infinity here, it will start approaching this line B. And this corresponds to the fact that B can be thought of as a point at infinity in this direction. And then the interesting thing is, if you go kind of to infinity here, you start approaching this line. And then if you go to infinity on the other side, you approach also this line, but from a different direction. In a certain sense, you kind of start out here, you go to infinity, and then you instantly start coming back from the other side and try to visualize this. And so we see in the projective vanishing locus, you have 2 points at infinity corresponding to these 2 lines here. And so this was basically, we argued just by staring at this picture, but we can also do some calculation. So what are the missing points on the complement of A2, well, the complement of A2 is the locus where x0 equals 0. And we can also do that substitution. So in this here, we can substitute x0 equals 0, then we get this equation. And this we can factor by the third binomial rule into these two equations. And then, well, the 2 points in P2, which satisfy that the 0th coordinate is 0, and then the other 2 coordinates are equal, this gives you this point A, or the 2 points are have opposite sign, this gives you this point here. And these A and B just correspond to these two lines. And in fact, somehow a cool feature, if we copy this picture here, is we saw going here to infinity gives you basically the same point as going to infinity on the other side. And similarly here. So in fact, as a kind of side remark, the real points of this vanishing locus, whatever this means to be a real point, in fact turn out to give you a circle, because if you identify this end and this end, this end and this end, then you get exactly such a circle here. And it's encouraging because the circle is a compact space, and one of the reasons we do this whole projective space business is that we want to have compact solutions. Okay, and in this picture here, we have seen that basically this affine vanishing locus of F and the projective vanishing locus of F, they are very related, they're very similar. Basically, the affine locus is a cone over the projective locus, at least in this geometric sense that we see here. And in the following videos, we're going to make this precise, what it means to be this cone over the affine locus. And then the good thing is we already know a lot of stuff about affine vanishing sets, and then this transfers a lot of information on the projective vanishing set.